If you see ds, you need to remember it's a huge square thing. ds is arc length dt, but arc length of what? And that's where students mess up quite a lot. Arc length of the derivative. So you can also write down r prime and then size of it, magnitude. Magnitude formula literally came from the arc lengths because size of the vector comes from the right triangle, so that makes sense. From right triangle, most of those formulas are coming from right triangle anyways. So you need to have this kind of formula sheet in better on the paper and then in your mind for the test. But again, I keep mentioning that most of us are visual learners in terms of location of formulas. If you have it on a sheet of paper and you're using it for months with all those formulas on a test, you first remember the location of the formula. Oh, it was in the right corner at the bottom, and then it shows up in your memory. It was proven scientifically that our brain likes visualization of locations. So you might not remember the name of a person around you, but you remember that they're sitting behind you on the left. Like the location is important for our brain. So that's why you should have a formula sheet, at least to visually remember it. And color coding helps a lot. So if I ask you to find the integral ds, you change your function and you start creating this huge square root with derivative square plus derivative square dt, and then you integrate. If I ask you to find integral f dr, that's a vector field line integral. So now it has different formula. And actually, that one is easy. It's just r prime dt. So dr is literally derivative of r, dr. And now I'm going to show a couple examples. Yes?
So, sorry, can you go back one thing? So, for the dx of dt, dy, dt, is that the derivative of the, so you have the r of t?
Yeah, this is r. Very good. Actually, this is a very good point. The question is, where is x and y are coming from? I think that's the question. So, steps, when we ask you to find each integral, step one, sometimes you have to create r. That's when we ask you to create parameterization. R equals x comma y, and it's a vector also. R, you have to create it. Usually that's parameterization. On the test, I will usually give you a circle because everyone knows to do the circle one. R cosine theta, R sine theta. In this case, R cosine t, R sine t, and R usually is given, so t is the parameter, called parametrization. Parametrization is not unique, but for circles, it's like very classical one. So when you have that R is x equals blah, 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 and y equals blah, blah, blah. And then you take the first one, differentiate with respect to t, the second one, differentiate with respect to t, square each, add together, put a square root, and you put each of them into your original function to change it to be in terms of t. Did this answer your question?
So,
it was not a question.
R is going to be like a vector of some sort.
Yeah.
So, I know it to be in terms of t.
R is in terms of t, yes.
Yeah, so do you take the x part, like the x part of that vector, like the I part?
Yes.
And then find the derivative of that?
Yes.
Okay.
Correct. Correct. Very good. Let me write this down. Very good. Good job. You're connecting different notations. That is the same thing as to say R is xi plus yj. Yeah. Good job. X component, y component. Yeah, very good. And see, those are the parts are confusing. So it's nice if people will be asking about that. Now, and this one, line integral over c. Same thing, you have to create your r. Usually we give you when it comes, no, sometimes you have to create it. If it's given, it's easier, then you just move on. You differentiate your r right away, change f, and so on. Recent one, Green's theorem. I realized I should show you some homework problems just to make your life a little bit easier. And then you can prepare for the exam more. Green's theorem made this like weird formula. Here it is. Apparently, there's more ways to find line integral over vector fields. Instead of doing the previous formulas, which sometimes is hard, parameterization sometimes is horrible. You can switch to double integral and use this formula. Let me put it like so. Second component over x minus first component over y, where f has those components, q and p. And since you already asked, now I will be writing everywhere qi plus, no. P goes first, Q goes next in the alphabetic order. Thank you. Pi plus Qj. Yes, keep an eye on what I'm doing. I do make stupid mistakes. Definitely, my brain is not completely recovered. Some of my pills making me sleepy, and I can feel it when I'm going to school. I concentrate. Don't get hit by a car. Yeah. That would be upsetting if I get hit by a car and we have exam. That would be like sad, and we have to reschedule it and whatever. So that was a new formula, and it is already on a test. Like we give you no choice but to use it. It's already on a test. So I will show you example on that, and then we're gonna go back to amazing triple integrals and review that. So let's do the new material first because it will help your homework. That is 13.4 Green's theorem. Green's theorem. The next level of Green's theorem is Stokes' theorem, and that's super important. Super important. People in the field of engineering, they do Stokes' theorem all the time. So, higher dimensions, basically. For example, example 1. If I give you an integral, and it looks weird. It looks like this, 3y dx plus 10x dy. That doesn't even make sense from the integral notation. This notation is only reserved for the Green's theorem. They basically combining direction from x and from y in upper dimensions. Like a flashlight, which I was showing you last time. This idea of a flashlight is A, cute, and B, just pretty cool. It was here. When you look at the 3D object from different directions, you can see one of them will be like the x part, the other one dy part, but they look differently. Shadow from each direction is different. So they're combining both in one integral via formula. And that's how this formula is working, because it does look weird. Like, what is this? It looks weird, but that's what they're doing. They're combining each piece together and putting equal sign. So let's go back and finish this example. Solve this integral using Green's theorem if or where C is a positively oriented circle, x squared plus y squared equals 1. Positively oriented. I know some of you will ask this question. What if it's negatively oriented? How should we do it? I did not put any negative orientation for the test. We will have negative orientation of the surface for the final exam, so that's quite enough. But in general, the formula for the solution, the formula x equals r cosine t and and y equals r sine t only works for the positive orientation, counterclockwise. If you need to change the orientation, you put some negative in those formulas. So that's your job to fix it, our job as people who do parameterization. So the formula says, this weirdo 3y dx plus 10x dy has a formula using Green's theorem, GTH, or GT, has a formula. We're going from single integral to double integral over d, and we're going to have d, take the second one, differentiate with the respect to first variable, take the first one, differentiate with respect to second variable, dA. And now, like, too many letters. Someone told me I liked math until everything became letters. Like, I liked math until numbers disappeared. That's exactly like why calculus 3 comes to be the first level of our upper level math. Like, there's lots of cool stuff behind this formula. So let's see what is doing. First of all, we switch from C to D. Very cool idea. C is a circle. Instead of going in a circle, we're gonna switch to D, and D is everything inside. Pretty cool idea. From single integral on top of the curve, we're switching to double integral on top of the area, or of area. Now, where is my Q and where is my P? Do you know? Like, okay, I know how to differentiate, thanks God, I learned that. But like, where those functions are, where P and Q are what? Like, what should I differentiate, right? That's how our brain works. Give me stuff to differentiate, I'll differentiate it, but where is it? For that, you need to remember the formula. Before we went to this formula, the other formulas, and that's why you should have a list of formulas, I told you. The previous formula says you can write down as P dx plus Q dy. That was a previous formula, so we're connecting all of these. That means this weird notation tells me that this piece is P and this piece is Q. P is attached to dx and Q is attached to dy. Does it make sense? What do you think? And then dA here is not to write dx dy. It's going to be the area. So we'll have to figure out blah, 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 the area of the circle and stuff like that. So P is 3y and Q is 10x. Does this make sense? That is weird. Like, you have to, I agree with you if you think that's weird. Like, all of this notation is weird, but it's extremely important and have lots of applications. Okay, well, now at least I know how to proceed. I will have double integral. I'll figure out the d later. Derivative of q with respect to x gives me 10 minus is part of the formula. Derivative of p with respect to y gives me 30 dA, like so. 10 minus 3, that's 7. And now you can figure out using polar or anything you like, Cartesian also, why not, of the circle. X equals r cosine t, blah, blah, blah. But actually, you don't have to, yes.
So you don't have to keep the dx dy?
Oh, we just, yeah, good question. So we did this. From this awkward looking formula, we jumped to this formula, and when I was jumping, it already disappeared. I would say it's actually like went down. Derivative just of x went down, and derivative of y went down, and now we know the formula differentiating the second component minus the first component. Did I answer your question? That's good. The question was like, where did the x and dy go? Yeah, the formula changed it. So we had it here, and then the formula put them at the end, and that's what my dA is. I'm just writing dA instead. Why I'm writing dA? Because now I can decide what to do. I can do dx dy, figure out from minus square root of stuff to plus square root of stuff. We did it many times. If you don't know what I'm talking about, you're kind of behind. Minus square root to plus square root. We did it last quiz and everything like that. Or you can do polar with r and theta, but you don't have to. So the cool part is that it is 7 naked integral over d, and naked integral just give you the area of the whole thing. So note, let's keep some space so we can finish. Note, naked integral from a to b, naked single integral from calculus 1 gives you the length of the interval. Of course, it's not like empty. There's 1 inside, right? Like I think you understand. Gives you the length of the interval AB of AB, and it's B minus A. Well, if it's double integral, guess what it gives you over D? It gives you area of D. So of course it increases the dimension. Triple integral gives you what? Volume, right? We actually had the formula. Triple integral of 1 dx dy dz gave us a sphere at some point and blah, blah, blah. So I don't have to parameterize anything. I just need to know the area of this D. Do we know what D is? So it's going to be 7 times area of D. Area of D. Let me just put it in parentheses. D. Which is, what is the area of D? Let's go back and see what D is. Okay, C was given as a positively oriented circle. D is the area of the circle. So what is that? Pi r squared. Do you agree? What is my r then? So let me go here. D is area of the circle, right? I'm going back here. X squared plus y squared equals 1. X squared plus y squared equals 1. Area of any circle is, just like you said, pi r squared. What is my r? Yes? 1, exactly. So area will be pi 1 squared. So I multiply by pi, and the answer is 7 pi. Like explaining it is longer than actually doing it. If you know what double integral means, and it means area of that area of that yellow thing over here, the D, then you just put pi r squared there. And that's easier than to actually perform parametrization. And if you have to perform, you perform, which I'm going to do for you right now in the second example. What do you think about that? Then let me do next example. This is your homework problem number 1 and number 2. And there are only 5 of them. So just like letting you know. Yes?
I was going to ask, like, what is the positive oriented part of it?
Oh, yeah. Positive orientation means counterclockwise. So, the opposite from the clock. That's positive. Internationally, everyone agrees. Who knows why? Why not to clockwise? Like, that's easy to pronounce. But somehow everyone around the world agreed to be the other way around. I think physics major messed it up, and then everyone had to follow. Like then geometry had to follow, and everything. So I think physics majors mess it up. I think some of the screwing devices, or what's it called that? Torque, right? They have the counterclockwise movement, and kind of after that, everyone had to agree with that. Yeah. And the way we screw the screws, lefty tidy, righty tidy, lefty not tidy. That's exactly, one is positive orientation, that one is negative. So yeah. And surprisingly, everyone agreed a long time ago around the world. That I think is pretty impressive, that everyone decided to stick to that. Yes?
Does that change the answer?
Oh yeah. Good question. Green's theorem. Positively orientation is, I remember it will be negative because we're going the other way around. Area will be the same. But I think we have to indicate the negative orientation with a negative sign. Yeah. I should check it at home, but that's how I remember it. Yeah. Good question. Yeah?
But if it's going like in negative orientation, it's going to be like,
Oh, just negative? Yeah, everything is the same.
Negative and the positive types, just to apply which one's negative and which one's positive.
So you just put negative on the answer, or no?
In this case, it's positive, but if it's in a negative oriented, then you put negative.
Yeah, that's what I remember too. If it's negative orientation, you have to redo how the circle looks like. So x, r cosine theta, and y, r sine theta are designed for the positive orientation. You have to make sure it's negative. So when the person is walking, to force the person to walk the other way around, you have to put some negative sign here or there and see if it works. So in general, people just change the sign, unless it's something more complicated, of course. Good. So why it matters, actually. Now probably I should mention why orientation matters. If you walk through the wind, and the wind is in this direction, you know it matters. Then the wind helps you. If you walk the other direction against the wind, the answer will be different. And we already agreed before, not only the sign of the answer matters. If it's big, if it's positive, then wind helps you. Negative, it's against you. 0, it's perpendicular to you. But also how big the number matters. If it's positive and big, wind helps you a lot, or gravity is dragging you somewhere. If it's negative and big, gravity is against you a lot. So that matters. That's why orientation matters. Finally, let's do this one. C is a positively oriented square. Positively oriented square. What are those? What is with those squares, right? So annoying. Just give me a parabola or circle. I think that's also for these problems I've created for engineers and physics majors to actually build physical objects with vertices. Use Green's theorem to find integral over C 5y squared x dx plus 3x squared y dy. Solution. So if you see this on a test, step 1, not to freak out, because that looks weird. I feel brain doesn't see it quite often. Why there's a dx and dy in one integral and it's not double integral? Doesn't make sense, but that's what the formula says. So you're telling yourself, you know what to do, it's okay. You know how to convert this integral into a new double integral using Green's theorem. It's going to be double integral over d, and you will have to figure out that later. And now you have partial derivative of p with this q with respect to x minus partial derivative of p with respect to y dA, and you'll figure out a later. So instead of c, which is a square, that doesn't look like a square, instead of the c that looks like a square, positively oriented, you will be working with d. That's why it's only helpful for the closed curves. Now you have to figure out what is p and q, just like last time. Take a pencil and sign. This guy that goes first is p because it's attached to dx. This guy that goes second is q because it's attached to dy, not because it goes first and second, because one is attached to dx and the other one is attached to dy. That's more important because I could switch the order. Now at least you know how to proceed. Equals double integral over d, derivative of q, and I don't want to rewrite it, and I highly recommend you not to do it either. You stare at q and differentiate with respect to x. What do you get? 3x squared y gives you 6xy. Amazing. I heard you. Minus. Now you stare at p, 5y squared x, and differentiate with respect to x, which is, with respect to y, which gives you 10yx. And then keep dA, and we'll figure it out in a second. Does this step make sense to you? Or, yeah, I don't know, actually, does it make sense? Because after this, we're going to do the limits of integration. That's a completely different story. But that is part of the formula, yeah.
So
For the equation, instead, the first term was the dy and the second term was the dx. Would the p and q be flipped?
Yeah. So the formula flips them, the order. That's why it's confusing, and that will be hard to keep in mind. The original formula have them in order: p dx, q dy. Green's theorem says, I know what to do with that. Differentiate the second one first with respect to x. Then differentiate the first one with respect to y. And put a negative sign. That's the form. And you see, we don't even have z-axis, so it doesn't work with upper dimensions. And Stokes' theorem goes there. So it's only two-dimensional in this case. And if you want to remember it using this formula, it's d dx. I think it goes here, d dy, and then p and q. Let's check. Q with respect to x minus p. Yeah, it comes from the determinant. det. You don't have to remember that, but actually that's how it looks. It comes from the determinant. Cross product minus cross product. And that's why they're flipped, because when you find determinant, you always do cross product first. So x and q go together now. And those are derivatives, partial derivatives. Very good question. Now, can we figure out the area of this square? Maybe. This time I will actually show you how to create the limits of integration. And then you can try and find the area while I'm doing it and see if the answer is the same. So we did successfully integrate. Now I want to write down actually what is that D and A doing. So I have, did you notice that 6xy minus 10xy is minus 4xy? Nicely simplified. Now, I want to have dx dy. Dx dy. For that, I need a picture. Many of you don't draw the picture for some reason for two-dimensional objects, but you should. Pictures everything. It's very important to draw a square. Yes?
Just like above, so is the first term always going to be p and the second one always going to be q?
In the original formula, yes.
Okay.
Let me show you this. See, I knew that is the confusing part. The original formula is p goes first. Also remember the alphabet. They're using alphabet order. P dx, q dy. And then Green's theorem says, okay, flip the order and differentiate. Yeah. So Green's theorem's mixing it up. But originally it was in order. X and Y in alphabetical order and P and Q in alphabetic order. In math, they're trying to be consistent with the order. Yeah.
But I also meant when you have 5y squared x.
Oh, that is not necessary, but we always switch x and y. Okay, that is a different question. The question was, do we have to switch x and y or not? Why did I put x and y? Yeah, you will not be taking points off, but international people try to organize it. It's easier to read. X, y, z is easier to process than z, y, x. You have less thinking there. So usually people order in alphabetical order. Yeah, thank you. So you draw a square and you put your vertices there. 0, 0, 2, 0, 2, 2. I'm going fast because I think you know how to draw the square. Here it is. And now either you just know the area of this guy. You can figure out the area. So you decide whatever is easier. Or I want to point out how to create D if you actually need to do that. If you don't know the area of the object, just like last time, we just multiplied by pi r squared because we knew what's the area of the circle. This time I will create it for you. So whatever is outside, and it's a good practice, whatever is outside can be a number. Remember, those are axes. X and y. Sketch the picture. If y is the last one, then y can have just numbers. Y is changing from 0 to 2. It goes up and down, up and down, up and down, from 0 to 2. So I'll write down 0 to 2. The one is inside are functions. X is running from a function x equals to a function x equals. Let's see what x is doing. x is running from a function called x equals 0. That's a vertical line. And until the function x equals 2. That's another vertical line. Because it's a square, both end up to be numbers. 0 and 2. But actually, those are walls. Now, because all integrals have numbers here, you can actually integrate separately if you want to. Equals. Anyway, you know how to integrate double integrals. So I'm not afraid of that. I just put through one question, multiple choice, just to integrate triple integral. So nothing to do that. You just integrate it. So triple integrals on the exam. So one question just to integrate. I think that should be like a good question too. And remember, your calculator can do a single integral. So you just need to integrate 2. And the last one, you can use your calculator. So either you break it into 2 integral, which you can do if all the limits of integrations are numbers. From 0 to 2 dy, from 0 to 2 dx. The first one will be minus 4y, and the second one will be x. And integrate each. And you get the answer minus 16. So did you check the area of the rectangle? See, did it match? Of course. So this was not a lot of waste of time to draw this square, but actually if you know the area, you can avoid doing this. Let me circle. This step can be avoided. You can skip, because BC, area of this specific square is what? What? Area. 4. Because it has length 2 and width 2, and it's also a square, so 2 times 2. It's 4. So actually the integral becomes like this. Minus 4 times area, which is minus 16. That is faster. But if you kind of hesitate, you can do anyway. Yes?
So, like, this one is not, like, a blank integral. Like, it has x and y in it. So, like, you can just kind of ignore that. And, like, you can still do it, like, the area method. Like,
Yeah.
the last part.
You can do it like last part. This time I want to do both ways to show you what I mean. So, in the previous one, we also could do integral and integral. Dx, dy. Y would be from minus 1 to 1, because it's a circle. X will be from minus square root to a square root. And integrate. And it'll be hard. So that one is for sure easier. Just avoid doing that. And write down the area, pi r squared. For this one, it was not too bad. So 0, 2, 0, 2. And you can check the result. But it's still much faster just to use the area of the square, which is 2 times 2, which is 4. 4 times minus 4 is minus 16. Nice. That is my review. Well, it's new material, you know, for the Green's theorem. Actually, I will stop recording here to have a separate video on Green's theorem. Questions? Very good questions, people, for the Green's theorem. Yes?
How do you know that A is equal to 4?
Yeah, thank you for asking. It's a square, and they gave us those vertices, so I just actually build it first, right? And such as a square. So I build it, and then I checked it is from 0 to 2, from 0 to 2. Find one side, 2 lengths, the other side, 2 widths, if it's a rectangle, side times side, square, side squared. So 2 times 2 is 4. Make sense?
Well, my question was like, once you have the area, then how do you know to multiply it by -4?
That's a good question as well. Okay, this is what I will tell you. Just a second. Let me concentrate. Okay, I'm ready. So we are going. The question is, this is a good question. We are right now at this moment, minus 4xy dA. This is what we did. We figured out minus 4 from taking partial derivatives. A is the area of this region D, which we're working on. So it will be like so. Oh, that's the good question. Basically, where did the x and y go? Yeah, we just plugged 1 basically. This is area of the square. So, oh, I see. You're asking like there was something inside. So how did we know?
I understand for the other one, it's 1, so you just move it out and then you just do the limits. But for this,
Yeah, with this one, do you know what the question is? Before, there was just a constant inside, so we kick it out. But now it's not. Now we actually had functions. So how did we just know that? That is a little bit odd. Yeah, I guess we should be more careful. I agree with you on that. Interesting, but it still worked. I should think about it at home. Why? Okay, then in this case, it's better to do limits of integration. We cannot kick out this out. Yeah. That's not how it works. You can only kick out the numbers. So, good point. Good catch. I did not notice that. Then let me put this as a question mark, and I'll check it at home. Somehow, like, I'm very sure it works, but I cannot figure out right now why. That's why I don't like teaching when I'm sick. I sometimes glitch. More questions? Okay, let me then continue with different material.